بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. أهلا وسهلا بالجميع في مركز الشيخ إبراهيم. Today we have two speakers and one lecture, and this is unique. One speaker is Professor Atef. Atef is coming from Egypt. He got all his degree from Egypt, BSc, MSc, and PhD, and he promoted at the university till degree of professor. After that, he joined the Atomic Energy of Egypt for years. 2006, he moved to EAEA, and he got many positions for more than 16 years or something, 18 years. Starting from head of the department and chair of committees, and he finished there 2020. After that, he moved to Jordan. Now he is a director administrative of SESAME, and all we know that SESAME is a project of the Middle East accelerator, and there is a lot of work is there. We hope that he will succeed in this project as he succeeded before. Our next speaker is Andrea Lucy. He's from Italy, and we all like Italy. Especially he's from Trieste, and really I like Trieste as a city. He graduated from Trieste University. I have been there many times to the Department of Physics. Also his MSc, BSc, and PhD from there. After that, after finishing this, he joined a project which is a collaboration between India and Italy, a beamline, which is related to SESAME also. And after this, he joined a project with the European Union in making some collaboration on scientific infrastructure. In 2020, also he came to Jordan. Welcome to the Middle East. He is now scientific director of SESAME. We are waiting the lecture. Thank you very much for visiting Bahrain, and thank you very much for helping people in the Middle East in order to engage in especially fundamental science and technology. Thank you very much, both. Please, you are going to start. Thank you.
Okay. Maybe I need just to get this pointer. Thank you, Dr. Muhammad, for this introduction. I don't know if maybe better I go down so I don't hide the screen. So what do you prefer? So because maybe anyway, I'm not very tall, so I'm not hiding the screen maybe. But okay, thank you, Dr. Muhammad, for this. Indeed, it's a great pleasure and a great honor also to be here in this historical center for culture, and actually it is opportunity for me and opportunity also for my colleagues to be here. Also, it is opportunity to introduce for you one of the important facilities in the Middle East, which is called SESAME. And SESAME is a joint venture. It's an international project, and it is located in Amman. So I will go directly to. Oh, it's not. So I have to. I don't know. It's not working. What? Yeah, it's now is okay. So SESAME stands at Synchrotron-light for experimental science and application in the Middle East. So this is the acronym of the name is called SESAME. And maybe we all from the region, we know about SESAME. It's very famous seeds. And these seeds, we make tahina. I think we all love tahina, which is made from sesame. And I think it was very good selection, and it was very good choice of this name. And I learned that this name was proposed by a Palestinian delegate from Palestine, and he proposed this name, Sesame, and after that the committee, they chosen and they approved this name because they found this name is attractive and maybe it's easy to pronounce, and to say Sesame is very easy to pronounce. Sesame is a light source. It's a source for light, and it is one of about 60 light sources around the world. But Sesame is the only one in the Middle East, and this is what we are proud of, to have such a facility in our region. SESAME is located at Allan. This is a small village, about 35 kilometers northwest of Amman in Jordan. Of course, you can find more information about SESAME in this website, www.sesame.org.jo. SESAME is a cooperative venture. It was established as the model of CERN. You know, CERN was established after the Second War in Europe, and it was cooperation between most of the European countries. But I know it's not, now it's international organization now. SESAME is developed in the same model, and it is established also under the auspice of UNESCO. SESAME is a third generation facility, third generation light source, Synchrotron-light source. It is officially opened on May, 16th of May 2017. And the heart of this facility is a 2.5 giga electron volt accelerator. This is the heart, and actually this is can provide a wide spectrum of radiation from the infrared, which of course the energy of infrared is low, and to the hard X-ray. This is wide spectrum of energy. And SESAME aims, of course, to foster the scientific research in our region, and also to make the cultural bridges between the diverse scientists from our region between the member states. And one of the very important aims of SESAME is helping to prevent and reverse the brain drain. Brain drain, of course, is a problem we are facing in our region, because most of the smart people in our region, they are looking for better opportunities. They are looking to maybe to find this abroad, not in our countries. So maybe they prefer to go abroad. But having such a facility, actually it attracts those people because they find some challenge. They can prove themselves in this high technology facility. So it is actually some of the brains who already left our region, they return back to SESAME. And also SESAME, this facility can attract even some brains from Europe. And you can see here our colleagues. We have Dr. Andrea Lausi, he is coming from Litra in Italy, and we have other scientists also from Europe. They are working in SESAME as international facility. But the question now, why we built a synchrotron facility? If we would like to have a regional facility in our region, why we choose light source? And actually there are some reasons for this. The light source can provide a wide spectrum of applications, the different thematic areas of science. It's from physics, chemistry, pharmaceutical, medicine, agriculture, and food, even energy, cultural heritage. It's a very, very wide spectrum. In all thematic areas of science, you can find some application in the synchrotron light source facility. And also light source facility can, as one of the aims of SESAME, is can build scientific and cultural bridges between, through the international bridge between the scientists in our region. And also SESAME is a user facility. And the meaning of user facility is that this facility is available and operating, and the user can come from any member state in the region, and they can stay at SESAME for 1 week or 2 weeks or few days, of course, based on his experiment, and he can come and use the beam lines and do his experiment and takes the results with him. And after that, he can go back home to work on these results for analysis. And of course, he can also, connect, can be accessed remotely to our facility to continue the data analysis of his results. And at the end, of course, he can publish the results of his paper. And here I can share with you this photo during the official inauguration, and you can see His Majesty King Abdullah, his Jordan king. And here we have also Princess Somaya, she's also with the prince. And here we have Fabiola Ginotti, she's the General Director of CERN. And we have here the General Director of UNESCO. We have the European Union Commissioner. We have Professor Rolf. He is the current president of the Council of SESAME, and he was the General Director of CERN. And actually, since SESAME was established, all the president of the council, they are ex-general director of CERN. And this can show to you the relation between CERN and SESAME. From day one, from the beginning of SESAME, CERN was there and was supporting this idea and supporting this project. Maybe I can go back to some history about this facility, because actually the idea came back to the 80s, when the Nobel laureate Abdus Salam, who was thinking about the need of the Middle East to have a light source facility. And he was speaking about this since the 80s. And after that, there is a committee which is called Middle East Cooperation for Science in the Middle East. This committee, with a number of European scientists, they also were discussing together how to promote the cooperation in scientific research in Middle East. And after that, they came with the idea is to move the BC1 facility from Germany to somewhere in our region. And this idea, after that, when the becomes solidified, and they agreed on this idea, and the government of Germany agreed to move this facility from Germany to the region. Jordan was selected to be the host of this facility after competition with other 5 member states in our region. So it is, I think this is just highlight about the history of this facility. SESAME consists of 3 accelerators. We accelerate electrons. We are not like CERN. CERN accelerate protons, because they are studying the proton collision. But here, we need to produce light, and the easiest way is to produce light by accelerating electrons. So we have 3 accelerators. The first one, called the microtron, this blue part, where the electrons are produced, and after that, the electrons has gained energy, and the energy of these electrons increased up to 20 million electron volt. After that, these electrons can move through this transfer line. This is called the transfer line number 1, and goes to the second accelerator. We call it the booster, where the energy of the electrons increased from 20 million electron volt up to 800 million electron volt. And when reaching this energy, the electrons injected through this transfer line, this is the second transfer line, into the third accelerator, which is called the storage ring. And inside this storage ring, the energy of electrons again increased from 800 million electron volt up to 2.5 gig electron volt. And the electrons can be stored, because everything is under vacuum. You know that to accelerate electrons, we have to be under vacuum. We cannot accelerate charged particles in the air, because air will stop the electrons. So the electron can stay here for about 24 hours in the storage ring. When we make this, the trajectory of the electrons to be circular, we have to use bending magnets. This is powerful magnets, can make magnetic field to affect the trajectory of the electron to be bent slightly. And all this, we have here 16 bending magnets, and the electrons move in circle. But at the bending magnet here, when the electrons bend, they lose some energy. And this energy is emitted in the form of light. And this light is cover, as I mentioned before, a wide spectrum of range from the infrared to the hard X-ray. And we can here build about 23 different beam lines around this circle. Currently we have, I can show you what we have now. Currently we have 3 operational beam lines called the infrared and the EXAFs and the material science powder diffraction beam lines. Those are 3 beam lines are operational. And the 4th beam line has been inaugurated in last June 2022. And it is under commissioning now, and it's in final stage to be officially operated, and will join the other operating beam lines very soon. And we have other 2 beam lines under construction. One is called the tomography beam line, it's called BEATS, and the Turkish beam line, which is called TechSpace. The BEATS beam line has been completely installed now. It is almost finished. We are starting the commissioning, and hopefully we'll do the official inauguration and official opening of this beam line in next June. So it is after maybe a few months, we will open this beamline. And after that, this Turkish beamline, which is under construction now, and we hope that we can open this officially during 2024. So next year could be operating. So these beamlines, of course, I will not speak about the beamlines because my colleague Andrea, the scientific director, who will speak in details about the beamlines and the applications and what is the benefits, what we do with this beamline. As I mentioned before, SESAME is a user facility. It means that we make a call for proposals. And all the scientists or the users from our region, they apply their proposal. And there is a committee to review these proposals and to select the best of the proposals. During the last period, we received up to 461 proposals, and 236 has been accepted. It's almost 50% of the received proposals has been accepted or have been accepted. And you can see here the proposals coming from different countries in our region, from the members. And also we have some proposals coming from the observer countries like France, Germany, Italy, Russian Federation, United Arab Emirates, United Kingdom. And also we receive some proposals from non-member, non-observers from countries in Africa, in Latin America. Because we are open facility, research is, as we all know, that science has no borders. Science has no nationality. Science should be open for everyone who would like to work with science. And this is the objective of having such international projects in a region like Middle East. The output of the work with SESAME is to make publications, to make scientific publications. This is the output. When you do and you make the results, you do your experiment, you get the results. After that, you need to publish this in the prestigious journals. So up to now, I had the record was 64, but I think my colleague Andrea told me today they become 65. But I got this record just a few days ago, but it's now, because the number is moving, so it is, you can see now the number of publication increases from year to another. So hopefully this year we will can even publish more publications. And actually, maybe you can find more details with Andrea. The type of publication and the impact factor of the journals is highly impact factor journals, and this is really important. Also, we have, as I mentioned, SESAME is a user facility. It means that the user will come from a member state and he will go to Jordan and he wants to stay to do the experiment. And of course, we cannot waste the time of the scientists to go to the hotel, which is about 35 kilometers in Amman, and spend 2 hours every day going and back. So we have the guest house in place so they can work 24 hours because the experiment is available 24 hours. And the scientists, sometimes they go just to sleep half an hour and go back to do the research, to continue the experiment and come back again. So it is a continuous process. So the guest house is a very important facility located in the premises of SESAME. And actually it was built by a generous donation from the Italian government. Actually, all SESAME was a generous donation from the European countries, actually, and the other light sources and the European Union. All the facilities, most of them, maybe the members paid only few amount of money in the capital budget, but the members, they pay only for the running cost to make the maintenance, to operate the facility. But most of the infrastructure there in the facility was donated by our friends in Europe. The guest house contains 48 rooms for guests. Actually, these rooms are well equipped. Maybe you can see some photos here. Yeah, this is the cost of the building. It's cost about 2.1 million euros. We received 1.75 million from Italy, and the rest was paid from SESAME budget. And also we received maybe about 50,000 to 50,000 euros from the Swiss embassy in Amman. And we have actually made something called the Swiss Lounge. We put the Swiss name on one of the meeting room in the guest house. You see here, these some photos for the guest house. This is the rooms. You can see kitchen, you can see dining room. This is a two meeting rooms in the building. And here, this is one of the very important facility. Because my presentation, I'm not going deeply in science, because I'm leaving this to my colleague Andrea, so I'm focusing on the infrastructure we have in the premises of SESAME. And one of the important facilities is the solar power plant. So SESAME is the first, and actually it is not only the first, it is the only light source facility in the world operated by renewable energy. And this solar power plant is located in a place about 30 kilometers from our place in SESAME. And this is because the area where the SESAME is there is green area. And we cannot cut the trees by the laws. This is forbidden by the government of Jordan. We cannot cut the trees in this area. So we found this place very close to the premises of this building is Jordan Atomic Energy Commission. It's called JAKE. And this is because Professor Toukan, he is the chairman of JAKE, and he is also the general director of SESAME. So he found this place, so actually he donated this place to SESAME to put this facility, and also we pay only a symbolic rate actually for the land, which is about 1 GD per what's it called, dunam. Dunam is 1,000 cubic meters, so it is symbolic rate, which is about 150 GDs per year. The cost of this facility, this solar power plant is $7.143 million US, and this was funded completely by the European Union. So thanks to the European Union, because actually they saved the SESAME. Without this solar power plant, I think it was SESAME couldn't be survive, because you will see later the expenses of the electricity in Jordan is very expensive, and that means that if we paid all the budget we have, the annual budget we have, it will be not enough to cover only the electricity bill. So we are lucky to have this facility. The lifetime of this solar power plant is 20 years. You can see here this is the capital cost of the. And I can show you maybe in the next slide just a comparison between what we are paying now and what we're supposed to pay if we don't have the solar power plant. And here, in some months there's less, because actually in 2022 we have too much of shutdown, because we were installing new 2 beam lines were under installment. And during the installation of the new beam lines, we have to shut the machine down, and because we cannot work while the machine is operational. So that's why maybe some months you can find this rate is less, but some months this is the normal consumption, which is about $450,000 US per month. So you can see this is only the electricity bill. I didn't speak about the spare parts. I didn't speak about the salaries of the staff. So you can imagine how much we are saving by this plant. And here in this table you can find maybe more details, and maybe the number. This is what we paid with solar power, and this is what proposed to pay. This during the 4 years since 2019 until now, until the end of 2022. And here what we saved 11 millions from this solar power plant. And the capital cost, it was only 7.1. You can see now we gained even more $1 million, and this facility is supposed to operate for 20 years. And so you can imagine how this project crucial to SESAME, and really very important SESAME, and this is saving our money and saving our resources, so we can use our budget for maybe upgrading our capabilities, upgrading our beam lines, and also improving the infrastructure we have at SESAME. Maybe this is my last slide, and after that I will leave the floor to my friend and my colleague Andrea. This is just a video, and this video will be only for 4 minutes about SESAME. I'm sorry this video was shot in 2019. Maybe you find some information here which is not updated, like the number of the beam lines. It's mentioned here is 2, but actually there are 3 or 4, almost 4 now. But anyway, it will give you a good idea about the facility. Where is the audio? It is not working? Or? Can you help me, please? Because there's no audio. Maybe here. Audio is working or not? Not working? Okay, I don't know if you can, this can help or not, but anyway, it will give you some idea. This is the facility, but the audio was very important to listen what he is saying. This is Dr. Professor Toukan. He is General Director of SESAME, and also he is at the same time, he is Chairman of the Jordanian Atomic Energy Commission. This is Dr. Ricardo. He was the Technical Director. He's not working in SESAME anymore, but he was at that time, he was the technical director during the shooting of the film. This some technicians in SESAME. This is the building. So I will try to explain to you what's in the video. Dr. Toukan again. And here, this is, of course, the location. Those are the members of SESAME. And Dr. Giorgio Paolucci, he was scientific director of SESAME before Andrea. He's not working anymore in SESAME. Of course, this is a bending magnet inside the storage ring. This is Dr. Jihan Kamil. She's the beamline scientist of the infrared beamline. Again, in the storage ring, this is bending magnet. This is a vacuum pump. Dr. Walid Zidane, he was the administrative director before me, so he's not working anymore in SESAME also. So the faces, most of the faces are old faces because it's 3 years ago. This is the location where SESAME is there. Here is SESAME. And you can see the area is green area surrounding to the facility. This is the control room. Yeah, Dr. Jihan walking, going to the air beam line. This is Abdullah and Hussein, they are operators. Ricardo again. Sufyan, he is a power supplier engineer. He is Jordanian, and he is working with SESAME. This is Adli, he's a safety officer. He's doing some safety inspections. He's measuring. I'm sorry, because the audio was very important to you, but I'm just trying to help. Yeah. This is a microscope in the infrared beam line. I don't know if I can. Mr. Omari, he was us here. He's here, sitting here. Masoud Harfouch, he is from Algeria, and he is the beamline scientist of the exact beamline. Yeah, Jihan from Egypt, by the way. So because I mentioned that Masoud from Algeria, so I have to to mention other nationalities. Abdullah is a control engineer. He's from Jordan. Anas is a control engineer also from Jordan. So Andrea, maybe you can come to take the floor. Thank you very much. Thank you.
Thank you. Okay. So thank you very much, Atef. Thank you very much, everybody, for being here. Thank you for the hospitality in this marvelous place. And I had a little tour of some of the houses here around. It's really a marvelous enterprise. It's something unique, absolutely unique. So while we see the last images of the movie, I will start saying that now my purpose is to convince you that something which is called synchrotron-light for experimental science and application in the Middle East, we start with this word, scaring word, synchrotron. It is actually something which is not used mostly by physicists. It is built, it has been invented by physicists, but it is now used by any kind of scientist or researcher in medicine, in biology, in archaeology, in chemistry, in physics, in material science, pharmacy, etc. So it is a sort of universal tool to make light on how is made the world around us. No, the other way. Yes, so 75 years ago, was 76, okay, that was last year's cartoon. 76 years ago, synchrotron radiation was observed for the first time in a small synchrotron in New York. This was light emitted by charged particles running in a circle, which is exactly the main ingredient of what we are doing, so the light bulb, if you want. And this works like after 75 years, this kind of machine populated the world. There is a huge cluster of machines in United States, another one even larger in Europe, and then Middle East is also well provided of this kind of machine. Apart of that, in the rest of the world, there is one machine in Brazil, one in Australia, one in Jordan, and one in India. So the quest for these kind of machines is rushing around, and there are good reasons for it. So to start explaining the effect, I will start explaining the basic phenomena that gives this light. And the basic ingredient is velocity. We are shooting electrons at the speed of light. So normally we know antennas. In antennas, we have electrons going up and down in a piece of metal. They go at 100%, at 1% of the speed of light, even less, and they provide radio waves which are going everywhere, in all directions. You know, in the movies in the 50s, you had these waves going around, starting from an antenna and communicating to the spy in the other country that something is happening, and so they could know that was going on. But this is because the electrons there in metal are moving very slowly. So the radiation goes in all directions. It's called dipole radiation. The same things happens here, but these electrons, with respect to us, they are moving at the speed of light. So this changes completely the geometry of the phenomenon, because due to, if you do the calculation with Einstein's relativity equations, you will see that all the power peaks in only the forward direction. And this is what makes, essentially, so unique synchrotron radiation, synchrotron-light, because it is very concentrated, just due to this extreme velocity. I mean, they are really fast. In 8 minutes, they would be on the sun. In 24 hours, which is the typical time of circulating in one of these rings, they do twice the round circle of the solar system. So it's a lot of space. And they are really, really fast. And they are emitting a very concentrated beam in the forward direction. There is another consequence which causes, because of this concentration, the uniqueness of this light. That is, you know, you might be familiar with the uncertainty principle of Heisenberg, in which if you know the velocity of a particle, you don't know where it is, or vice versa. The same happens with energy and time. We have the same equation. So since we see this blip of light for an infinitesimal time, so a very, very short time, because if you stay just in the plane of the orbit and you look at this electron which is going around, you will see the emission, which is a very tiny laser-like, it's much more parallel than laser, blip of light, then this disappears immediately, which means that on the other direction, so in the energy space, you need a lot of energies to describe it. So the radiation covers a very wide spectrum of, a very wide ambitus, a very wide range of energies. So, and these two ingredients, there are many other characteristics. The fact that it's polarized, it is time structured, it has a million characteristics which are nice. You can calculate everything out of it, so you can predict exactly the shape of the beam. So all these things make it a unique source. But the two major ingredients are that it is very collimated, so it will be possible to put a lot of energy in a tiny spot of your sample, and it has a wide energy range, which makes it feasible for any kind of interaction. We will return on this point. So, nowadays, a facility is not anymore that tabletop thing. It is something much larger, which occupies a building. The buildings are very often in the form of a donut, just because this is the shape of the thing. They are composed, as we have seen for SESAME, they are all the same. There is some injection system, a transfer line which brings the electrons in the main machine, and then there are the bending magnets which make it rotate around. So generation 3. Generation 1 was parasitic use of colliders, of machines like CERN. Generation 2, machines built for the purpose of producing synchrotron radiation. Generation 3, okay, there is a lot of space between the bending magnets. In this space, we can build other magnetic devices to tailor the radiation, change the wavelength, the peak of the wavelength, or select something different, push the energy higher, and so on. These are called insertion devices and are the characteristics of the third generation, like SESAME. It started at the beginning of the 90s. A fourth generation is being built in this moment, in which we put more bending magnets, because we discovered that if you put more bending magnets in the orbit, then the size of the electron beam stays more compact. And this again will allow us to obtain so that if the source is smaller, the beam will be smaller. So it's all in the quest of a higher and higher and higher brilliance. So how many photons in a small spot? Outside the ring, there are the beamlines. The beamlines are they are called this way. They are the objects which bring the light from the ring to the experiment. You can think of them as objectives, like a photo camera. The objective of a photo camera, which concentrate, will tame the radiation which is emitted by the ring, and bring it, select the energy, change the geometry, focuses, defocuses, what is needed for that particular experiment. And we can build beamline which can use infrared, ultraviolet, vacuum ultraviolet, soft X-rays, hard X-rays, all kinds of radiation can be used to observe in different ways the samples. So this is the key point where we go from only physics world, we have spoken of effects in physics, to something wider. So, because the photons impinging on a sample, depending on which wavelength they have, which energy they have, they will generate different effects. So, a photon can be absorbed by the electrons in matter, and then the decay will generate a fluorescence photon again. And this tells me which kind of atom I am talking to. So it gives you an elemental analysis of the sample. Or it can be absorbed, and we instead observe how much it is absorbed. So this is a radiography, or this is a more sophisticated EXAFS. We will return on that experiment, which tells you where the atoms are. Then, or it can, if it has a very short wavelength, so hard X-rays, it will normally undergo diffraction. So there will be a sort of, it will be actually an elastic event in which no energy is given, no energy is taken, but the summing up the interaction of the beam with the atoms in the sample, you got diffracted to a different angle. And by collecting how much intensity goes in which direction, with some mathematics, since more than 100 years, we are able to know where are the atoms in the sample. So this is a technique which was invented in 1913 by Laue and Brach, and this thing is what allowed us at that time to know that in kitchen salt there is one atom of sodium, one atom of chlorine, one atom of sodium, one atom of chlorine in a square net, and 50 years later to discover that the DNA is an helix, and nowadays study viruses and hope find out what is the shape of these protein spikes in a COVID virus, and find out also ways to fight against it. So, extremely powerful technique, diffraction. Everything all pictures that you have seen anytime, where are the atoms in matter, comes from diffraction studies. Not completely. Some electron microscopy is putting its tail in it now. And then photoemission. Photoemission is the phenomenon for which Einstein got actually the Nobel Prize. You know, this relativity was not perfectly convincing. So they debated for many years in Stockholm if to deliver him this Nobel Prize, and then they find out this solution. Okay, we will give him the Nobel Prize, but for this photo emission. So a photon passes and electrons take the energy and are emitted. If you measure the photon, the energy of the electron, you know everything of the electron after this event. You obviously have built a machine which we have seen cost 100 millions or something, 200 millions, 500 millions. So you know everything of the photon that you have sent in to the sample. So you do the difference and you get the energy and the momentum that the electron had when it was in the matter. So again, another mean for doing an analysis, a chemical analysis of the sample. So altogether, these are all tools to explore with this probe, to explore matter. Any kind of matter can be a piece of metal or some archaeological remain or a medicine or a protein or a bone, whatever. So, and this is why around synchrotrons, these are populated by these objects, these beamlines and experimental chambers, which are totally different one from the other. And new ideas come continuously to exploit this light in different and new fancy ways. So, all in all, for the sake of all these kind of activities and more, synchrotron light sources really are scientific centers which are continuously evolving. And where the access, as we have seen, is granted on the basis of proposals. So it is only the scientific excellence that will bring you to obtain beam time at a synchrotron. Okay, a few examples from the recent past of SESAME. I don't even tell you which beamline, but we studied catalytic reactions on a substrate to find out what is the best catalyst between rhodium and cobalt to transform glycerol in syngas. This was a Turkish group. Or a Jordanian group in the Royal Scientific Society is studying metal-organic frameworks. So the structure of metal-organic frameworks, how they change with temperature, and because these are functional materials that can perform various kinds of tasks, from absorbing CO2 to retaining water, which is typically a quite important resource for this region, capture water from the atmosphere. Or medicine, so observe the variations in the proteins, so in the chemistry of the proteins of this macrophage, which is associated with tumors. Or again, digging in the past of humanity to find out that this mummy had a disease in the skin. Cabeza Egyptita. This is an Egyptian, this is a Maltese, Greek, British group which is studying an Egyptian head which is kept in a museum in Spain at a synchrotron in Jordan. It's fantastic, yeah? Not only synchrotrons are community inside themselves, but also altogether they form communities. LEAPS is one example of that. The closest cluster of synchrotrons is in Europe, and all these facilities cluster together in order to get a critical mass for new development, new technical developments essentially, and also to have a stronger voice with the funding agencies in Europe, obviously. This was the the attempt for sure. And SESAME is actually a member of this League of Accelerator-Based Photon Sources, LEAPS. This is SESAME, how it looks like. We have already seen it. So this is a central ring. Inside here are the booster and the injectors, and below this white wall, star-like, which is concrete, which separates us. So it's a radio protection wall. Is the machine, and the beamlines are coming out tangent to the ring in all directions. So as you see, there is actually space for many more. We hope to fill it as soon as possible. So this is how it looked like in the drawing. And let us start, let us go around a second and let us explore them, starting from bending magnet number 2 for the IR beamline, and then go all around and look at the EXAFs, material science, BEAS, HAZAP, and TEXPES. So, infrared. We have said that all these beamlines are tangent to the main ring. We have seen this drawing everywhere. So it goes tangent. And obviously, the first beamline that I show you goes radially. But this is just because we have a mirror here. So the radiation is emitted tangent to the bending magnet, and here there is a mirror which projects it radially outside. Outside, there is a laboratory for infrared, which is exactly the same kind of setup that you find in a laboratory for infrared in university. No difference, the same kind of spectrometer, the same kind of microscope. So why at the synchrotron? Look at the difference. This is with the, so I told you that there is you get better if you use a synchrotron. So it's a pictorial demonstration of how much better. So this is 500 seconds, 1000 scan with the laboratory source. The same sample in 16 seconds, 32 scans with the synchrotron. Just because the beam is much more collimated. The source is much more brilliant. And so the signal-to-noise ratio is incredibly better. So you can do things in a synchrotron that are simply impossible at a laboratory. So this is why it is in continuous evolution, because we can do more things. So we can get new ideas and do things different. Not only better, but also different. This was the first paper from the IR beamline. This an investigation on tissues from placenta to find out if it's possible to get some clue on how to foresee this horrible disease, preeclampsia, which is so difficult to be foreseen, to get an early diagnosis. Then we turn around the beam, the ring. We meet BM08, the EXAF's XRF beamline. This beamline uses fluorescence to get information, and EXAFs. EXAFs is a rather complicated technique, if you want, which again tells you where are the atoms. The important thing is that in order to do EXAFs, you need to be able to change continuously the energy of the impinging photons. So the function that you are going to deal with is the absorption as a function of the energy of the impinging beam. This you cannot do in the laboratory because you don't have a continuous source in the laboratory. So this is a totally native technique of synchrotrons. And by looking at these oscillations, you know where are the atoms around the emitter. It's bit complicated how it works, but it works. And it can be applied for many studies. You can study glasses, for example, because you don't need to have a crystal, or you can study a catalyst. Oh, calendar? Okay. No, I understand. Yes, I got it.
Sorry.
Thank you. Okay, so this is a Turkish group which did the same experiment that we have seen at the beginning. So catalyst for finding an efficient transformation of glycerol to syngas in presence of CO2. It's not moving anymore. Okay, next beamline, diffraction beamline. So diffraction, as we said a few minutes ago, it's an elastic scattering, an elastic event in which photons change direction. So the experimental chamber is made like this. There is a sample in the center, this powder contained in a capillary, in this case, and around it, you can move a detector measuring the angle. And so you measure which intensity at which angle. And this gives you a lot of information that you can then exploit. So this is what you can get. You get a curve like this. And from the analysis of this curve, you can know position of atoms, so you can have let's say a structural analysis of your sample going from atomic level all the way up to microstructural. Really a lot of information if you look carefully at it. And the fact that the beam is very parallel allows you to look much better than with respect to the laboratory. This is an example from the kindly contributed by the Canadian light source, in which you see this is a sample taken in a laboratory where there is an enormous amount of amorphous, so 90% of the sample is not crystalline, so it does not produce these sharp peaks, which are the secret of diffraction, but only a large lump of data. And this masks completely any kind of structure. So the signal to noise ratio here is horrible. You go to a synchrotron, the beam is much more parallel, and then, hey-ho, you get a very nice curve, which by subtracting this shape, you can then renormalize and get all the peaks very well separated between them, very clearly and very well. So this is something, again, you cannot do this kind of samples in a laboratory. You need a synchrotron to do that. This is one of the various experiments done at the MS beamline. This is the first publication. The MS beamline has been opened in December 2020, so I would like to point out how heroic has been the staff of SESAME in working in a very difficult situation, because they could not stay in two of them at the beamline at the same time, obviously. There was COVID, masks, etc. So one had to go in, the motor technician had to go in, change something, then go out, and then the beamline scientist could go in and check if it was all right, and then go out again. So it was really a heroic task, which was very well repaid, because this beamline has an exceptional record in few time between measuring and publishing, actually in a extremely high impact journal like Argumentative Chemie or ACS Materials Letters like this one. So quite a story of success. The future. We are finishing beats the beamline for tomography at SESAME is a European project, is a European grant for the construction, for the design and the construction of a model beamline at SESAME. To the set of partners of this project, which is led by the European synchrotron radiation facility, the large synchrotron in Grenoble, this partnership contains also ALBA and Solaris, which are younger, not as young as SESAME, but still younger facilities in Europe, which do not have a tomography beamline, or were building a tomography beamline like ALBA at the time. They participated in the project just because then the follow-up would not only be the beamline at SESAME, but also the drawings and the design and the scientific case and the details for building their own beamline. This is being a community. And so this is where, so this is a computed tomography beamline. So I remember you, every hospital has a few of these machines. They do radiography all around the sample, the human being in this case, by moving the detector and the source around. Something that we obviously cannot do, so we do the opposite. We keep the source and the microscope fixed and the detector fixed, and we rotate the sample. Differently from here, we can go to submicron resolution in space. Here we are stuck at sub-millimeter resolution. And this photo arrived on my WhatsApp today, and is the beam. It's not a fluorescent screen. This is green paper. So they are not looking at the beam while staying there. And this red mark here is where the beam has arrived at the very end of the beamline today for the first time. So we are really closer to be opening the beamline to users. This is Gianluca Abdelrahman. Oops, poor Gianluca. Gianluca Abdelrahman and Yazid from the various, so mechanical engineer and aligner, motor electronic engineer and beamline scientist all together, and quite happy, I must say. This is HESEB, the beamline that has been inaugurated last year in June. This is a donation from a cluster of Helmholtz associations in Germany, so Dresden, Berlin, Jülich, Karlsruhe, and Hamburg, and with a financing of 3.5 million euros, they built for us this beamline, which is the first beamline with for soft X-rays. You see that there is no hatch around. The soft X-rays are confined in the pipe of the beamline. That's more than enough. And at the end, there is a simple, relatively simple experimental chamber, which allows you to do the same things that you do in the EXAS beamline, but with soft X-rays instead of hard X-rays. So with the EXAS beamline, you explore where the K edges, so the hard edges of most materials. Here you go to the L edges, which are related more to the chemistry of the sample, because they are outer electrons, so they are in electrons which are mostly involved in chemical bonds of the molecules. Nearby, we have started to see a change in so one of the consequences of having a synchrotron radiation source in the Middle East, that is the first beamline built in the Middle East, designed and built in the Middle East. That will be TechSpace. This is a funding that 4 institutions, 3 universities, and the TENMAC, the atomic energy, office in Turkey have obtained from the presidency of Turkey to build a branch line to HESEP. Branch line means that they will share all the first part of the beamline from the source down to the monochromator, and then after the monochromator, HESEP has two mirrors. One directs the beam to the HESEP station, and when moving, you can instead direct it to this new beamline TechSpace. This is a typical way of using soft X-rays beamlines, so in pairs, because in the ultra-high vacuum of the beamlines, it's time-consuming to change something, so you get a better duty cycle if you work on one beamline, prepare the experiment on one beamline while using the other, and vice versa. So because the time is a bit time-consuming to work with ultra-high vacuum, and this one will provide a photoelectron beam time. The experimental chamber, which will arrive in April 2024, and we will test it directly on HESEP. We just changed the experimental chamber. This will allow us to have a full set of beamline with also photoelectron emission. Again, it's this action. Yes. Okay. So this is just to show that it works better if you turn it on. So this is the number of publications per year before and after opening the beamlines. So you see here, and this starts to explode. And this is the quite comforting histogram of the impact factors. So the average impact factor of the papers from SESAME is around 5. It's higher than 5 actually, and 20% of the publications constitute this second peak here of high impact factor papers. So a quite reassuring status, which it's more than comforting. I am enthusiast of this because these are numbers more similar to a mature facility than a facility which is starting, and this testifies the goodness of our beamline scientists, but also of the community around it. Obviously, this is again a common work. We have training and events continuously. We try to do the best, and I will finish with these few notes. So it took a certain amount of years to build it, but now SESAME is an internationally well-connected reality which produces world-class science, and we are continuously working to improve both our commitment to training in the region and to increase the portfolio of instruments and beamlines. And with this, I thank you for your attention.
Just at the end, thank you very much to Professor Atef and Professor Andrea for this nice lecture and all this information about SESAME. This is very new to us. Hope that this project will continue for years. If there is any comments, yeah.
Thank you for this very informative talk, and didn't get the chance to attend it all, but we had a discussion morning about it. What about about the training? You skimmed through a slide that included training in SESAME. So what are the type of, let's say, internships that you have? Do you have any program offered by SESAME itself that maybe students can get enrolled in, either undergrads or postgrads? So what are the type of training that you offer in SESAME?
Okay, at the moment we are concentrated in schools, and so either online or in presence. There will be, and there have been, a lot of chances of coming for or attending for 1 or 2 weeks or few days to a focused school. So in 2019, I came to SESAME just to direct a school on environmental physics. And this is where I discovered that Giorgio was leaving, and then he put this in my ear that why don't you apply? And so this is how I started considering coming to SESAME. And so this goes continuously. About internship, we have some internship of master students from Jordan in the machine sector. So they are coming and they are staying for 1, 2, 3, 4, 5 months and work together with the technicians and the engineers in the technical sector, which is, so this I didn't say. We are divided into 3 great categories, 3 great assemblies: the administration, the scientific sector, and the technical sector. This is typical of all machines of this kind. So we are at the interface between big science and laboratory science, and the big science people clusters in the technical sector, and the laboratory people clusters in the scientific sector, let's say. So we are the beamline, and there is this wall between us and the machine, which everywhere is existing, and we do our best on a daily basis to overcome the wall and to bring it down, but it's there.
Okay. So you mentioned that you have topics, and for example, you did a training in environmental physics. What other topics do you provide? I'm a physicist, so my interest is mainly in physics. But
so the next 2 schools will be dedicated to HAZEP and to BEATS. Mm-hmm. And in 1 year from now, there will be another general school. We do this together with the ICTP, with the EAEA, and the Cyprus Institute. We cluster together a school which goes for 2 weeks online on everything that you would have ever known about a synchrotron, starting from the basic equation of dipole radiation, down to how you bolt the last bolt of the beamlines, and start to get measurements out of it. But this year we will host. We are starting to do also something. We are testing in various directions. So this year we will host 2 students from Bahrain for 8 weeks, actually it was CERN who invited us in joining them in this adventure, and I'm very grateful that you did, because I think it will be marvelous. And actually to the 2 Bahraini students we will add also 1 student from Palestine and 2 students from Istanbul University, just to have a little group to talk to and to introduce to them. But this will be again a general course, so they will move from one beamline to the other for 1 week, and also have a couple of weeks for the training in the technical sector, because there is a lot of fascinating stuff going on there. So there are alignment, power supplies, radio frequency cavities, they are all vacuum and cooling, all those kinds of things are quite interesting and make up a good CV for.
Yeah, really interesting. Great opportunity. Thank you so much.
Thank you. Just continuing on the question of Ali. So these students you are going to put together this summer, do they have a specific background? I mean, are they just physicists or are they engineers?
There's one for physics and one, the two Bahraini, I mean. This one is for physics, from a physics studies, and the other one is IT. So it's a computing student. And because we have also a strong group of for the IT. So actually, the Palestinian and the second Bahraini will go with our IT engineers, and the other three will go on the beamlines. And it's synchrotron. Not as much as CERN, but at the end you need a lot of computing in order to deal with all this data. So it's an IT-intensive facility.
Just I have a simple question. There is time limit for this to work. I mean, there is an end, and we will have a new one because this is old, you know.
Yes.
Came from Germany.
Yes.
And the energy is 2.5. So there is a new generation for future.
The new generation is putting more bending magnets. In the case of SESAME, I think that the best option would be to go greenfield. So to build a new machine, completely new machine. Obviously, when we will have the shoulders, so the community has to evolve up to the point that the machine is needed.
And also we hope to visit there to see the site.
More than welcome, everybody. We are open.
Any comments, please? Okay, at the end, thank you very much for this nice night for both. And we are very, very pleased. Thank you very much.
Thank you.
Of course, I would like to invite you. Of course, I would like to invite you and invite anyone from Bahrain University or from Bahraini scientists to come to visit SESAME. Ms. Mariam also, I think we agreed to arrange a visit maybe to SESAME. Yeah. Thank you. Thank you very much for the hospitality and.
Gift for you from.
Yeah. Okay.